Hey, calc folks, I wanted to go through this number 27 from the homework. We haven't done a lot of application problems. We haven't taken the time for a lot of that, but I kind of dropped one into the homework here, and it's there's quite a bit to tackle on it on the algebra part. So I'm going to work through this and just put the video up. I'm going to get pushing along on working through this anyway. Get this going. Number 27 from 14.8 is what I'm talking about, which is economics application of trying to maximize something when you have a constraint. So it's a Lagrange multipliers problem, which I really like that technique, but this is a tough one to work through when you get the equations written down. So I'll show you what this ends up looking like. So we're looking at maximizing this function, p, which is supposed to be b L to the alpha times k to the 1 minus alpha. So we got a bunch of letters going around, both English and Greek ones. We'll get to that.
Send me a link. Where are you? Have I? Okay, it's YouTube, right?
Yeah. Okay, so the constraint that we're working with on this also has some other letters in it, so we got to keep track of what's going on. That's lowercase p. So, and this is capital P up here. I want to emphasize what's going on here. This is my function of L and K on this thing. There's our constraint. So this thing with your constraint is always going to be your g function, what we call g function. Usually g of x, y, but in this case, those are our variables. So the constants, the things that we're treating as constants in this are the alpha, the b that's in there, the m and the n, and lowercase p are just constants. And we got to keep that in mind as we go through this, what's moving and what's not. We have to solve for, well, we're going to have a lambda in it because the Lagrange multiplier we use lambda for, we kind of can solve for that, but it's the L and K that we're trying to find. Nice thing about this is it's a proof problem. They kind of tell you where you're supposed to end up. There's formulas for L and K that we're supposed to end up with, but we got to get there showing that that's a maximum on this constraint line here, which is a simple thing. So normally with the Lagrange multipliers, you got gradient f equals lambda gradient g. This time our f is p, and this is, I'll call it g anyway, the constraint function. Both of those, well, we got to do the derivatives on both of those things. So I want to write down, first of all, what gradient of g is. That's a function of L and K. And you're just talking about this thing. So the derivative with respect to L, partial derivative with respect to L is just m. And the partial derivative with respect to k is just n. So that one's simple. Let me get that written down. Gradient p is a little bit more calculus work. This is the one step where we've actually got to do a little bit of calculus. We're going to do the derivatives on this. So I want the partial derivative of p with respect to L. These other things are constants then. Derivative with respect to L, it's just an exponential. Not an exponential. That's the wrong word for it. It's just a power function. L is the variable. Alpha is a exponent. So regular power rule for this thing, it's going to be constant multiple alpha L to the alpha minus 1 would be your derivative of that with respect to L. Times this, we're treating this as constant, so that's still on there. Constant multiple of that. And then do the same thing with respect to k right here. So that's still constant multiple with respect to k. And then this minus 1 would just be a minus alpha. So we'll have 1 minus alpha, capital K, to the negative alpha. I subtracted 1 from the exponent. That's what I got left there. That looks good. That's my gradient P and gradient of G. So I can set up my Lagrange multipliers formula. Just says that this equals lambda times that. So I'm going to turn that into two equations, and then I got my constraint equation up there. But this is equal to lambda times this. So I've got B alpha, L to the alpha minus 1, K to the 1 minus alpha equals lambda times M. And this one, B 1 minus alpha, I'm kind of sorting things out a little bit, but the same expression equals lambda times N. So I like this as a nice introduction to what happens when you really have a long, complicated problem. What this Lagrange multipliers can end up looking like. So we need to solve for really L and K. Lambda is the third variable in this, and it's got to satisfy these two equations and the constraint thing that says ML plus NK equals this other constant lowercase p. This has got to be true also. We'll use these things, put them together somehow. So somehow 3 equations and 3 unknowns, L, K, and lambda are the unknowns. Tough algebraic situation. But one place to get started in this is these are it's pretty easy to get lambda by itself in this thing and substitute or set things equal to each other here. So I'm going to rewrite these things to get lambda by itself. It's one thing I can isolate easily. B alpha, L to the alpha minus 1, K to the 1 minus alpha over M equals lambda. And from the other equation, this over N equals lambda also. So these two things have to be equal to each other. That's kind of a substitution, or set these two things equal. And so this becomes B alpha, L to the alpha minus 1, K to the 1 minus alpha over M equals B 1 minus alpha, L to the alpha, K to the minus alpha over N. These two things have to be yikes. We can simplify this down thing a little bit here. We can see that the B doesn't matter. B is a multiple on each side. So dividing both sides by B, those actually cancel out. That's okay. And then a little bit of simplification using the exponents on this. And we'll work it from there. Okay, I do have this written down. I'm trying to work through it again. But I noticed I can simplify it. I got powers of L on both sides. I can divide by the smaller power of L, which is alpha, L to the alpha minus 1. If I divide both sides by that, it's going to be gone from here, and I'm going to leave an L to the 1 on this side. So let me just write this out this way. I'm dividing by L to the alpha minus 1. Those cancel. Subtract exponents here, and you get a positive 1 now. So yeah, let's keep track of what we got so far. I'm going to do the same thing with the K's there. Keep track of all my pieces. This is going to be just L to the 1, so that worked out nice. I'm going to do dividing with the K also to simplify this down, so I can divide by the smaller exponent here, which is the minus alpha, and leave a K to the 1 on that side. So those will cancel from here. It leaves K to the 1 here. So I got alpha K over M equals 1 minus alpha L over N. We're getting a little simpler finally. I could solve for either K or L right here and make some substitution if I wanted to. I've got a nice relationship between them. So keep track of this. I'm going to actually get, okay, that's how I do one or the other. I'm going to get K by itself. So K equals M1 minus alpha L over N times alpha. So I divided by alpha on this side and I multiplied by M on that side just to get to K by itself. Now I can do another substitution. That's the key thing when you're working with a system of equations. Nonlinear equations. You can't usually cancel like terms, so you're usually doing substitution quite a bit. I'm going to substitute that in. My third equation, which I haven't used, my constraint equation up here that said mk plus ml plus nk equals p, right? We had this before. That's lowercase p, the constant. So that's a relationship between L and K. If I make this substitution, I can solve for something here. So I'm going to replace K with that whole expression. So ML plus N times that whole thing equals little p. And that's M1 minus alpha L over alpha N equals p. So the N part comes out. That's nice. And I have an equation with just a bunch of constants now and L that I can sort of factor out on this. I got a common factor actually of ML. I'm going to factor that out. That's 1 plus 1 minus alpha over alpha. That's all I got left when I factor out the ML. So I'm going to simplify that. We're getting somewhere. Eventually, we're getting somewhere else. But I'm going to go ahead and do this addition. That's alpha over alpha plus 1 minus alpha over alpha. So that's what I get with a common denominator there. It just comes out 1 over alpha. ML times 1 over alpha equals P. And so L equals alpha times P over M. And K, I had K solved for up here, so come back to this now that I know what L is. I'm going to solve this on out. K is supposed to be M, 1 minus alpha over alpha N. So you kind of keep coming back to use what you know up here. A bunch of equations involving the same stuff, but this simplifies quite a bit. Alpha. Got 1 minus alpha over N times P. Something like that.
Yeah, I'm just out. Working along.
Which I believe is exactly what we're supposed to end up with. Those are the two values to the thing. So you got to persist with something like that and keep using the equations, kind of substitution, and trying to rewrite things and work your way down to isolate what you're trying to solve for here. Those are the relationships that we're supposed to. That's L and K in terms of the constants in the problem. And that was what we were trying to establish there to prove. So I hope that's helpful. The other problems using Lagrange multipliers are not nearly as bad. Algebra, but setup is the same deal. Your constraint equation and your two, or however many variables you have, your equations from the gradient equals lambda gradient equation. Put things together and work things out. So I'll put this up and we can talk more about these later on.